Second half of chapter 2. Let's get cracking. We are going to talk first about how the neurons in our brains communicate. We've been talking about brain structure so far in a sort of global sense, if that makes any sense at all. We've been looking at it at the entire brain and the different lobes and some of the different structures within the brain and what they do. But if we were to sort of zoom in, all of the structures of the brain are made up of individual cells called neurons, right? Neurons are the basic building block for all of our um, our central nervous system and for the peripheral nervous system as well. All of these nerves are neurons, right? Those two words are more or less interchangeable. A nerve cell is a neuron, and vice versa. Um, and we want to know how those work because essentially all of the communication that our brain does, everything that our brain does, is based on the action of those neurons. Those are the cells that actually send messages to each other that get you to move your arm or to smile or to think about what you want for lunch today, or anything that your body does. It is governed by the action of neurons. So, how do those neurons work? What do they do? Well, you can see a couple of neurons right here, right? They are cells like all of the cells in your body, where they have a cell body and then a nucleus in the middle, but then they have some branches coming off of them that most of our cells in our body don't, that make them look a little alien, but they are human, very human in their nature. Um, these branches off from the cell body, there's two different kinds. There are dendrites and there are axons. Um, the dendrites are the receiving end. The axons are the sending end, right? So each neuron will have only one axon but can have multiple dendrites, right? Um, so you can have these short branches that stick out just a little bit that will link up to other neurons from, to other axons coming from other neurons, and so you can receive multiple inputs, that one neuron, from a variety of different neurons, because you can have multiple dendrites. The axon, however, there's only going to be one of them, although that axon can split and have multiple terminal points. So even though you've only got one axon, it actually meets up with several other neurons down the line in terms of meeting up with different dendrites down the line. Okay, now receiving, sending. What are we receiving and sending? Electrical impulses, essentially. That is the primary way that these neurons interact, although it's a little bit more complicated. That there is an electrical part of the communication, and there is also a chemical part of the communication, and we'll talk about both of those. And what I really want you to understand from this discussion is how exactly that communication works. Okay, so that's what we're going to talk about. Now, your neurons are not the only cells, or not the only type of cell in your brain. You also have what we call glia cells, which are the helper cells of the brain. They don't engage in any electrochemical communication like the neurons do. They are instead the cells that form the scaffold in which the neurons are sitting, right? So they form sort of a structure to keep all of the neurons in place. And additionally, they form what we call the blood-brain barrier. Our neurons don't connect directly to our blood supply in our brain. The glia cells take nutrients from the blood and then pass them through themselves onto the neurons. So the glia cells actually form the blood-brain barrier because they will filter out the majority of parasites and bacteria and viruses that might like to get to the neurons. Those instead will get stopped at the glial cells. Now, it's not a perfect system. There are some viruses and some chemicals that can bypass the blood-brain barrier, alcohol being one of them. We talked about that one a little bit last time. Um, so it's not a perfect system, but it does protect the neurons, which are pretty much the most important cells in our body because they run the system, right? They're the control center, and so we want to protect them as best we can. So we form this barrier with the glial cells. Now the glia cells have another function as well. Yes, here it is. Some glial cells they have branches just like the neurons themselves do, but these branches, rather than connecting up with other glial cells, will wrap themselves around the axon of the adjacent neurons and form a protective barrier that we call myelin, the myelin sheath, right? So I talked last time about myelinated axons versus unmyelinated axons, and essentially this is what we're talking about. Some of the transmission cables, for lack of a better term, which are these axons, get wrapped up in an insulating sheath, and that protects them from damage. It also serves to speed up the communication as it moves down that cable, and we'll talk about how that happens here in just a little bit. But the axon is essentially, I'm sorry, the myelin sheath is essentially just little bits of glial cells that have wrapped themselves around that axon. It serves as a protection. In fact, we have a variety of diseases that attack the myelin sheath. What happens then, so multiple sclerosis is one of these. You get the body's own defense mechanisms attacking this myelin sheath because it doesn't recognize them suddenly as part of the same body. It sees the myelin sheathing as a foreign invader, and so it attacks it and strips it away. What you get in that case is when the axon gets exposed there, then it suffers from scarring, and with enough scarring on an axon, it can essentially shut that axon down so that it can't pass a message anymore. And that's what happens with multiple sclerosis. Over enough time, with enough scarring built up, different neural pathways shut down, and you lose some of the functions of your body more over time as more and more of this scarring builds up. I actually had an aunt who passed away from multiple sclerosis, and it was a long, difficult process for her. Because of the older she got, the fewer things she could do. She got to the end of her life, and all she could really do was blink her eyes, yes or no, in response to questions, and was entirely bedridden, couldn't move herself. So really difficult to deal with. But that is one of the things that our myelin sheathing is meant to prevent. Okay, now, whether you've got a myelin sheath or not, let's talk about how the communication between neurons occurs. I mentioned that there is an electrical impulse that travels through the neuron and down the axon, and we'll talk about that in detail here in just a second. But let's talk about the other aspect of it first, the chemical aspect. When the electrical impulse arrives at the axon terminal, which is the tail, and you can see it's sort of blown up here towards the bottom of the slide. When you reach the axon terminal where it meets up with another dendrite, those don't actually touch, right? They're not linked together. Instead, that dendrite and the axon terminal are just barely separated by what we call the synaptic gap, or more simply, it's called the synapse. That is the meeting junction between two neurons. What happens is, as this electrical impulse arrives at the axon terminal right here, then what that electrical signal does is it triggers the release of vesicles full of neurotransmitters, which are chemicals, essentially, that our body creates. They're held in these little vesicles that then migrate to the terminal itself, merge with the cell wall, and dump their neurotransmitters into the synaptic gap. These neurotransmitters then drift across the synaptic gap and lock on to receptor sites on the adjacent dendrite. Now, these receptor sites in the neurotransmitters fit together like lock and key. If you get the right neurotransmitter meeting up with uh, the correct receptor site, then they will fit together, and what that will do is that will open up that lock fitting into that key will open up channels in the surface of the dendrite that allows charged particles from the exterior of that dendrite to then flow to the interior of the dendrite, and that then does something that we'll talk about here in just a second. But that's the chemical transfer between two neurons. The axon terminal dumps its neurotransmitter into the synaptic gap. It crosses those neurotransmitter particles, cross the synaptic gap, lock onto receptor sites, which then does something on that dendrite that causes the electrical signal to then propagate in that adjacent neuron. Okay. As you can see here, your axon terminals can split and go in different directions. We saw this actually a little bit last time when we were talking about interneurons and how you can have, what am I trying to say? Reflexive responses to things without necessarily thinking about them. That is possible because that axon right there at the junction in the spinal cord splits, right? So it has one branch that is going up the spinal cord towards the brain, and another that serves as the interneuron that then links the sensory neuron to the motor neuron that then allows your muscle to flex so that you can pull away from the hot stove or step off of the Lego or whatever it is. That is how that works. So you can get a single nerve impulse that can travel to multiple different places and trigger multiple different responses simultaneously because these axons can split halfway down the line and because you've got multiple axon terminals as well. Okay, so I talked a little bit about our chemical signaling already. Let's talk about the electrical signaling. I mentioned that when the neurotransmitters lock onto the correct receptor sites, what that does is that opens channels in the surface of the dendrite itself to allow molecules that are in the intracellular fluid to flow into the dendrite. What happens is the dendrite, the interior of a neuron at rest, is slightly negatively charged. Okay, when these channels open up in the surface of the neuron, they allow positively charged sodium ions to flow into the interior of that neuron. That then creates a change in the electrical signal. If enough sodium ions come in from outside, then it changes the electrical signal inside that neuron at that one specific spot from negative to slightly positive. And that's what we can see here. We actually call it the action potential. And you can see we're sitting at negative 70 millivolts in terms of electrical energy inside the neuron while at rest. Some of these sodium channels open because neurotransmitters have locked onto the receptor sites, and suddenly you get more positive ions coming into the interior of the cell. That then causes what we call depolarization. Once enough positive ions are inside the neuron or inside the dendrite at that point, it causes a chain reaction where all of the sodium channels in that spot open up and positive ions flood into the interior of the cell, and it causes this spike in electrical activity, or I guess I should say electrical charge, from negative up through 0 to positive. It peaks right around 40 millivolts, right? Now, as it reaches close to this peak, the cell membrane of this neuron recognizes that it is reaching its maximum positive capacity, It closes the sodium. I'm sorry, that doesn't happen yet. What happens is it starts to open up adjacent channels, different channels that allow potassium ions to leave the cell. Now, potassium ions are also positively charged, and so when those leave the cell, then um, that restores the balance, the slightly negatively charged balance that the neuron wants to maintain when at rest. So once these potassium ions are leaving, then first the sodium channels close. You can see that right at the peak, and then down when you get into the refractory period, where it is even more negatively charged than usual, then the potassium channels close and you come back to a resting state. This all happens in less than 3 milliseconds, so it happens very, very quickly. And what happens is that this occurs almost like people doing the wave in a football stadium. Remember when we used to go to football stadiums and actually, be near other people? And yeah, that was fun. Anyways, it has to happen in a wave action. So if you're in a football stadium, you're not just going to stand up all by yourself and go, woo, for no good reason, right? You wait until a wave is starting and you can see the people, 20 rows that way or in one direction or the other. They're all standing up at the same time and going, woo! And so when it gets to you, then you are supposed to stand up and go, woo! Unless you're a person like me in which you're like, I'm not doing this. Nevertheless, you're not going to stand up and do it all on your own. You're going to wait for the people around you to do it. In the same fashion, similar fashion, the sodium channels in the neuron itself, right there at the dendrite, are only going to open once the adjacent channels have opened, right? Because you get this, once enough sodium ions are inside, you reach this point of no return that we call depolarization, where all of the other channels have to open. And so when that happens at one spot along the dendrite, and you get this change in electrical signal, that then triggers the sodium channels in the adjacent section of that dendrite to do the same thing. And so you get this wave movement where the channels are opening and you get this wave of electrical change moving along that neuron. One spot after the next, each one adjacent to the other until it moves through the cell body and into the axon, and then that change in electrical signal travels down the axon until it reaches that axon's terminal, at which point the electrical signal will trigger the release of the vesicles full of neurotransmitter, which will then dump the neurotransmitters into the synaptic gap. And the same process happens all over again, because then those neurotransmitters lock onto that adjacent dendrites receptor sites, open up the sodium channels, and it all happens again, right? It is a cascade effect that travels from one section of the neuron to the next, and it is what we call an action potential, because that change in electrical activity has to occur in order for any action to happen. Now, I mentioned earlier that the myelin sheath actually speeds up the electrical signal. Here's how that works. When you have myelin sheathing on an axon, that wave action that I was talking about only happens in the unmyelinated sections in between the myelin sheath. Those unmyelinated sections are called the nodes of Ranvier. You will probably be tested on that. The action potential in a myelinated axon only occurs at the nodes of Ranvier in the unmyelinated spots, because essentially what happens is when you've got that myelin sheathing, it's covered. Those channels can't open, and so essentially that change in electrical activity jumps that spot, right? Whether you want to think of it going over that spot or under the myelin sheath and then jumping to the next spot. Because all of those channels in between don't have to open, then it jumps immediately to the next spot where there are exposed channels, and that's where those sodium channels open and the ions flood in, and that whole process occurs. But because it's only happening at some spots along the way, that electrical signal can travel up to 20 times faster in an unmyelinated axon. Excuse me. It will travel up to 20 times faster in a myelinated axon than it will in an unmyelinated axon, where it has to do the wave at every single spot along the way, and it can't jump over anything because there's no myelin there. Okay? So myelin makes the electrical signal travel faster because the channels are not opening where you are covered up with myelin, right? Okay. Now, this is the process that I already talked about. It just shows it a little more closely, right? You get the electrical signal arriving at the axon terminal. This triggers the release of the vesicles full of neurotransmitters, and those neurotransmitters then migrate to the surface of the synapse, merge with the cell wall, dump their neurotransmitters into the synaptic gap. That's not everything, though, because if you think about it, there's more to the process than this. If you just dump your neurotransmitters into the synaptic gap and they're just floating around in the synapse, well, then those neurotransmitter particles are free to continue locking on repeatedly to receptor sites and opening up those sodium channels. Generally speaking, we don't want this to happen. We want our neurotransmitters to do their job and then get out of the way. So there's a couple of different processes that happen to clean up our neurotransmitters, to sort of mop the floor in the synapse, so to speak. The first is what we call synaptic reuptake. Reuptake is the process by which those neurotransmitters then drift back across the gap, back to the axon terminal, and then are reabsorbed into the axon terminal and put back into vesicles so that they can be reused, right? We don't want to waste our neurotransmitters. That's good stuff, right? So it's going to be vacuumed back up, essentially, by the axon terminal. That's the process of reuptake. Now, that won't get all of the neurotransmitters, and there are cleaner cells in the synapse and in the intracellular fluid at large that will break down stray neurotransmitters into their component parts so that that material can be reused. But the primary process that I want you to know about is reuptake. We actually have some drugs that that depend on this process, right? So there is a class of antidepressant called selective serotonin reuptake inhibitors, more commonly called SSRIs. These drugs keep reuptake from happening for particular neurotransmitters, specifically serotonin. That's why they're called SSRIs instead of something else. So they are selective. They only work on serotonin. But what they do is keep serotonin from undergoing the process of reuptake into the axon terminal. What does this do? Well, for people who are depressed, one of the things that we know that we've discovered along the way is that folks who suffer from clinical depression or depressive disorders tend to have low serotonin action in their brain. They have less serotonin than the usual individual. And so what we do is give them these SSRIs that prevent reuptake from happening as effectively at the synapse. What that means is that their serotonin particles are hanging around in the synaptic gap longer, locking back onto the receptor sites repeatedly, and so you're getting more action out of those limited number of serotonin particles than you normally would. This seems to help stabilize mood in these individuals who have less serotonin than they normally should, right? You've got less serotonin than usual, so let's give you this drug that makes that serotonin work harder than it normally would, and that will help you manage your mood and stabilize your mood. And it does it specifically by targeting the action, the reuptake action for serotonin. Now, there are other antidepressants that do different things. There are some that that target norepinephrine. There are some that target multiple neurotransmitters simultaneously, but it's the same process for all of them, where they are preventing the reuptake of neurotransmitters that we know to be involved in mood regulation. Now, as you can tell, based on that little factoid that I just told you, the process that I have described for you just now, in terms of the electrical signaling as it moves through the neuron and then the release of neurotransmitters into the synapse, I am glossing over a bunch of stuff. I am giving you the quick and dirty version of electrochemical communication, because there are different kinds of neurotransmitters that do different things. The basic difference between neurotransmitters is whether they are agonists or antagonists. Now, you may not be familiar with those words in this context, right? Antagonist, we usually use that word to talk about the bad guy in a movie, right? That's not what we're talking about here. And you've never probably heard the word agonist. What we mean by that is what does this neurotransmitter do? Agonist neurotransmitters lock onto receptor sites that propagate further signaling, further electrical signaling in the exact way that I was just talking about a little bit earlier. Antagonist neurotransmitters send a stop signal instead. Right? So we have, as I mentioned, multiple receptor sites on the surface of our dendrites. Each axon terminal only has one type of neurotransmitter itself, but you can have multiple axon terminals meeting at the same dendrite at the same time. And what that can do is, if you have an agonist neurotransmitter and an antagonist neurotransmitter being released and locking on to the same dendrite at the same time, what the agonist neurotransmitters are doing are opening up sodium channels to say, hey, send this signal that I just received, right? This electrical signal, it's getting sent further. However, the antagonists, when they lock onto their receptor sites, they're closing the sodium channels, essentially saying, don't send this signal any further. We want it to stop. Now, why would it be useful to stop a signal from being sent? Well, sometimes we don't want the signal sent, like pain signals, for instance. Pain signals are very important, but not in every situation do we want them to be dominant, right? So you have certain neurotransmitters, like our endorphins, for instance, that are designed to block pain signals. They act as antagonists on those pain pathways through the brain. And so they are shutting down that signal. They are not allowing it to be passed. Now, if you have both agonist and antagonist neurotransmitters showing up at the same dendrite, how do you know whether the signal gets sent or not? Well, it's whichever of those neurotransmitters there's more of, right? If you've got more antagonists, then the channels will close and the signal stops and is not sent any further. If there are more agonist neurotransmitters, then that signal will be propagated and then will pass down the adjacent neuron in the fashion that I described to you earlier. Okay, hopefully that makes at least a little bit of sense. Really, what I would like you to understand from this section is what is the chemical. What is the electrical part of the communication for neurons? What is the chemical part of the communication for neurons? And sort of the basics of how both of those processes work. Okay, that's exactly what I was just talking about. All right, let's talk before we finish up here about the endocrine system. Because so far we've talked mainly about the action of neurons within the central nervous system. I mean, the same process holds true in the peripheral nervous system as well, but there's an entirely separate system of communication in our body. Excuse me, sorry. That does not depend on neurotransmitters or neurons. that still influences our behavior. I've made some mention of it already in the last chapter when I was talking about the sympathetic nervous system and the action of glands and hormones. That's what we're going to talk about now. It's our endocrine system, because our endocrine system does at least as much to influence our behavior as our central nervous system does, right? Okay, now what are we talking about here? We are talking about the glands in our body that produce chemicals called hormones that then travel to other parts of our body to send messages to that downstream part of the body to say, hey, you need to do something, right? Now, some of the important glands in our body that I would like you to know about, that you may be asked about. You've got the pineal gland in the brain that helps regulate your sleep cycles and your circadian rhythms, when you fall asleep, when you wake up, how you feel when you wake up. Pineal gland is responsible for monitoring those systems and releasing hormones to help modify those rhythms, right? The pituitary gland is sometimes called the master gland of the body. It is directly, it's very close to the hypothalamus, which we talked about as being the thermostat of our brain, right? The hypothalamus is what signals the pituitary to then send hormones to a variety of different glands and organs throughout the rest of the body to do a variety of jobs. So the pituitary does a bunch of stuff, right? It influences our growth and regulates the activity of other glands, tells those glands to either produce more hormones or produce less hormones, depending on the status of the body at that moment, right? Your thyroid gland is actually right here behind your Adam's apple if you have one, but still right there even if you don't. That helps regulate the metabolism in your body. I actually have to take thyroid medication every dang day because mine doesn't work right. So that helps regulate how much cellular respiration is going on in your body. How quickly are you burning through your energy and through your reserves. Your adrenal glands are so your adrenal glands, actually, you don't think about them much. They sit right on top of your kidneys. They look sort of like little sorting hats. And they release the adrenal hormones, right? Adrenaline is what we used to call it. Now, epinephrine and norepinephrine are the official names for those hormones. The adrenal hormones help us regulate and adjust to stress. They do have some implication in sexual functioning and overall physiological arousal. So those do a lot of work there. And then you've got the pancreas, which releases insulin to help you manage blood sugar, right? That's another one that you've got a lot of folks who have to take regular insulin doses because the insulin in their body is not functioning properly. Now, also not listed here on the slide, but also very important are our sex organs, which produce androgens and estrogens, the sex hormones in the body that help not only with sexual function but also with body maturation, right? So that we grow into adult size and shape and form. So all of those sort of work together, and it's this entire system that travels through the blood. These hormones travel through the blood in order to allow our body to receive the signal so that different organs and different glands do what they're supposed to do in a variety of situations, so that we can maintain homeostasis and grow as we are supposed to. The pituitary gland, as I mentioned, is frequently called the master gland of the body because it regulates the action of most of the other glands and organs that I was talking about. It gets its marching orders directly from the hypothalamus, which is right nearby in the brain. And we have, just like we have a variety of different neurotransmitters that we'll talk about this semester, we also have a variety of different hormones that do different jobs in the body in different locations at different times. So endorphins, I mentioned. The word endorphin is actually a portmanteau, meaning it's a mashup of two different words, meaning it comes from the words endogenous morphine. So endogenous means inside the body. We produce morphine in our body. Awesome. uh, we create chemicals in our brain and in our body that actually they function in the brain, but they also function differently at different spots in the body as a hormone um, that help us relieve pain and produce happiness and pleasurable sensations. Um, and it functions in exactly the same way that morphine does. I don't know if you have ever had morphine, if you've ever gotten hurt badly and had to take a ride in the ambulance and they gave you morphine. I have. I actually stalled out a four-wheeler going up a steep hill, and it rolled over on top of me, and I thought I had broken my back. I did not, thankfully. It was just very badly bruised. But they bundled me onto a stretcher and into the ambulance and drove me off to the hospital. And I was in extreme pain, and so the EMT that was with me gave me a dose of morphine until they could get me to the hospital. And I was very upset at the time. I was in a lot of pain, and I may have said some unkind things to that man. And then the morphine hit my system. And everything was cool. I was so glad to be there, and suddenly the pain just went away, and I was super chatty, and he had actually, done the IV not quite right, and so I was bleeding down the inside of my arm, and it was dripping onto my clothes, and he was like, "Oh, I'm so sorry," and he's wiping it up and, taping my stuff down and everything, and I'm just like, "It's fine, man, we're good." And then I got to the hospital and got my x-rays, and it turns out that my back was not broken, thankfully. At any rate, that's our body produces that same type of chemical, and if you have ever experienced a runner's high, that is the action of endorphins in the body, right? That's your body responding to you subjecting it to long-term pain by running long distances. What our body wants to do, it thinks we're hurt, right? Because you've got all of these pain signals coming up your ankles and your knees and your hips because you've been running for the last, 8 miles. And one of the things that our body tries to do is to shut down pain signals so that we can fix the situation, right? We want to not shut down due to a pain response if we need to close a wound or get to the hospital or whatever the case may be, right? Of course, idiot runners, sorry, I'm not really talking about you. It's just how I think about running. Runners take that reprieve that they're given where their body's like, "Oh crap, we're getting hurt. We gotta figure this out. Flood us with endorphins." And runners go, "Oh, that feels amazing. How about I run another 10 miles?" Okay. Anyhow, I don't know if you can tell just looking at me, but I go to great lengths to never string 2 miles together. So that is one class of hormones. You can see some of the other ones here. Melatonin is primarily responsible for helping us modulate our sleep-wake cycles. Epinephrine and norepinephrine work together. Those are arousal hormones that are associated first with fear and second with anger. Epinephrine and norepinephrine that help us respond to stressful situations. And then thyroid hormones, as I mentioned earlier, help us regulate our metabolism. Now, each of these, or at least some of these, endorphins in particular, can function as neurotransmitters if they are present in the brain, or as hormones if they are present in the blood and traveling to different organs in our body. So a lot of these are real multitaskers, but we talk about them and want to know what they are because they help us, or I guess I should say they are implicated in our behavior, right? You are going to behave differently with a high level of endorphins in your blood than you will without, right? And hopefully I'll get the chance to talk about some classic studies that have been done over the last century or so, where we make reference to some of these things. Okay, I think that's all we are going to talk about for this chapter. Yes, that is the end of our slideshow. So please go ahead and get Chapter 2 Smart Book assignment done and out of your hair. Get that discussion assignment done, and so that you stay caught up. I know this stuff isn't actually due until September 12th, but you will do yourself a real favor if you just stay caught up with the assignments and don't leave all of those things from the first 3 weeks until September 12th. Okay, thanks everybody. I will see you next week, and as always, if you have questions or problems and you're not sure what to do, please just email me and I will get back to you as soon as I can. All right, thanks y'all. Have a good one.